There's a number of things going on here in chapter 8. And so I'm going to go over this. The chapter is oxidation and reduction. And you'll see that this is actually a really important concept for a lot of things that we're going to be talking about as we go through the rest of the course. So again, this is still one of our background chapters, but also still very important. So we're going to go over not only what redox is, or oxidation reduction, but also how it's used, in particular batteries, for this course, and introduction to a bit of physiology, which we will come back to as we go. So with this first slide, what you're seeing here, of course, is rust. And that is a redox reaction. And I'm going to show you the equations involved with that. Again, here, you don't need to memorize the equations with this, but understanding the concepts about what's going on and what and how things work is what the operative importance is. And then in the homework, of course, I'm going to ask you more specifics and that will relate more directly to these details, but because that's where you can practice and you can look things up. All right. So oxidation reduction, and as you could tell, I already shortened it to redox. And these things always occur together. You can't have oxidation without reduction, and you can't have reduction without oxidation. So when we're looking at this, and usually what we're focused on is the flashy part, which is the oxidation. But and that's because we notice it but very often with the reduction, it doesn't look as interesting. But suffice to say, they are an important partnership in each one. So for every oxidation, there is a reduction. But how do you know what happens? All right, and I mean, this one is burning. I mean, that's the most common one that we have, but all these redox reactions don't necessarily involve burning per se. I mean, burning as a chemist, you're using oxygen and it's redox, but not all of them are actually using oxygen. So how do you know when you are having some sort of a reaction, right? And here, I love the way your textbook does this, is burn and unburn. And usually, like I said, you think of burning as consuming oxygen and making a flame. But like I said, redox doesn't necessarily do that, all right? So, so let's look at how you can tell. So there's these 4 ideas, and they're related, and it really all comes down to this one that's in green: the loss of electrons and gain of electrons, all right? But you can see this manifestation of loss or gain of electrons through these other ideas here, okay? So when you're looking at oxidation, I mean, since oxygen is right in the name, pretty much if you're gaining oxygen in your chemical reaction, then that's an oxidation, right? That's pretty intuitive. So if oxygen is going to the thing that you're looking at, it's been oxidized. But in order for that to happen, you must have lost oxygen somewhere, right? So you have the 2 sides of your equation, and so there's going to be a transition with the loss of oxygen and the gain of oxygen. So the loss of oxygen then consequently would be the reduction. The other way around, you don't usually think about this, but as a biochemist, I'm very familiar with this idea. And I'm going to, as we get through this talk, I'm going to, highlight that. But, when I know of a reduction, I always think of gaining hydrogen as a biochemist. And that is another way of looking at that. So in oxidation, you're going to lose that hydrogen, and the reduction is going to gain the hydrogen, all right? And then here, like I said, losing electrons or gaining electrons. So loss of electrons, you've lost negative charge, so you've become more oxidized, or more positive. So, the loss of electrons is the oxidation, and the gain is reduction. And we're going to look at this a lot when we're looking at batteries. But again, I said, as a biochemist, you know, there's another fundamental that, you know, drives physiology and biochemistry, which I'm going to show you in a little bit. Now, I said that you've lost electrons and you gained electrons, so you've gone from, you know, a charge that you know, you've made things more positive or more negative. And the way you can see that in chemistry is when you're looking at your reactions is you change your oxidation number. So, you know, we were talking so far on, you know, the charges of ions. So that charge on an ion is actually its oxidation number. All right. Not everything is an ion. So I'm going to explain to you how this works. There's some rules involved. And indeed, you know, I'm not going to make you do this part. This is harder to do. I'm not going to make you do this on an exam, but there's going to be some stuff in the homework where you can practice this, and you know, we'll do it a bit in class, just so you can see how it works. All right. So, so let's look at these a little bit more carefully. So, the gain of oxygen, and which is your oxidation, and the loss of oxygen is your reduction. So if you're looking at this chemical reaction, of course, there's two sides to this, right? So the gain of oxygen, so that obviously what's happened now is that during a chemical reaction, you've taken in oxygen. So the gain of oxygen is going to be more evident on the product side. So you can see here, there's an oxygen attached to the carbon. So we made CO2 here. And indeed over here, you can see that this carbon didn't have oxygen attached to it before. So you can see that obviously carbon has been oxidized in this case because you've gained oxygen, all right? Now on the other side of that, right, the loss of oxygen would be the reduction. So the reverse reaction would be the reduction, all right? So all of these things if they go the other way around. But in here you can see the gain of oxygen, all right, or the loss of oxygen. All right, so if this reaction was going the other way, you would see that. So now on the other side, right, you could see the loss of hydrogen or the gain of hydrogen. All right, so here you can see that this carbon has lost its hydrogen as it came over here to become CO2. All right, so you can see that that one has been oxidized, whereas over here now the water are now attached there. So you can now see that the gain of hydrogen, you can see that that in this case the O2 has now been reduced to water. Okay, so that's, you know, again, gain of oxygen, loss of oxygen, and loss of hydrogen, gain of hydrogen. And here you can see that both of those things are valid in this particular redox reaction, all right? So the other thing here, so this is talking now about electrons. So as we said over here, right? So you lose electrons or gain electrons. So lose electrons is oxidation and gain of electrons is reduction, all right? So here we have loss of electrons is oxidation, gain of electrons is reduction. And the way to remember that is Leo the lion says grr, right? So you can remember that. And you know, and this is, again, this is really what's happening in a battery and also is happening in biochemistry. In biochemistry, as you learn to be a biochemist, you learn how to do this thing called arrow pushing. And arrow pushing is you track the movement of electrons in different chemical reactions in your biochemical compounds. But basically here, you've got an oxidation because you've lost electrons, and that electron has to go somewhere. So here you have where it went, all right? So here's the oxidation, here's the reduction. And, you know, we say the thing that accepted the electron was the electron acceptor, and that's the thing that has been reduced, right? And then one would be the electron donor, which is the thing that has lost the electron, has been oxidized, okay? So, and you'll see when we talk about batteries in a few minutes how that works, all right? Now this one doesn't necessarily involve hydrogen or oxygen, you're just looking at the movement of electrons, but the movement of oxygen and hydrogen also involves the movement of electrons. So this is why I said this particular one takes place regardless, right? So here you see that the oxidant, so an oxidant is something that oxidizes, all right? So that means that it really likes to take electrons. And a reductant is something that likes to accept electrons, all right? And here you can see there's this reference to oxidation numbers, right? And in the way it has worked is that chemists have, what they've done is they've set up a table of tendencies of different types of molecules or elements for their ability to accept or receive electrons, right? And I'm going to come back to that thought in a few minutes. But when you're looking at these ideas, all right, understand that what's happening chemically is that some of these chemicals, or so these atoms are, and as I said before, oxidized. But in order to do that, very often as they lose or gain electrons, what's changing is their oxidation number. And when you get, and this is something you have to practice, right? So I'm not going to say that I loved doing this when I was in becoming a chemist, and indeed I'm a biochemist, so I have no great love for this, but it works really well. And if you try to, like the ones that I give you for your homework, just try it and look at it a bit as a puzzle. So if you're a puzzler, you might enjoy this. I don't like puzzles, so I'm not one that really loves this, but it's really important, fundamental to understand about chemistry. All right. So here's just a general chemical reaction. And notice there's no oxygen involved with this, all right? But you can see that there's a change in the charge or the oxidation number of these different substances in the reaction. Now, how do you know what the oxidation number is? Well, there's a few rules that you work with, all right? So I wrote the rules down on page 2, and it's handy to have a periodic table when you're doing this. When you're doing your homework and you encounter one of these to practice, make sure you pull that out because it will help you. And I have one in my notes for class, all right, so you can see how to do it. It's not hard, especially with the compounds that I'm going to give you. I'm not going to give you anything too complicated, but the one in my notes uses nitrous acid as an example, all right? And basically what you need to do is as soon as you see something like an element, all right, there isn't a straight up element here, but say zinc or something like that. If you just have a zinc solid, so straight up element, that is going to have an oxidation number of 0. Okay, and here you can see, Br2 liquid, right? It's not just bromine, but here you can see it's existing as an entity into itself. So we can say that the whole thing here overall is 0, right? So we'll say that when you see bromine or an element of some kind, the oxidation number is 0. So you see bromine and iodine, even though that there's 2 of them here. We say that the iodine is 0, okay? Now, the other rule is that if you see hydrogen or oxygen in a compound, okay, if you see straight up hydrogen, it's going to be an element again, 0. But if you see hydrogen in an element, its charge is going to be, or its oxidation number is going to be +1, okay? And oxygen, if you see straight up O2, it would be an element, so it would be 0. But if you see oxygen in a compound, all right, its oxidation number would be -2, okay, or -2. Okay, so here we don't have oxygen, but you can see we've got hydrogen, and here you've got an oxidation number of 1. So in each case, this hydrogen is 1, okay? Now, when you have an ion, all right, so if you have an ion, there isn't an example here, but if you have a straight up ion in a in a chemical reaction, its oxidation number is going to be equal to the charge that's on there. All right. So later on, you're going to see some examples where we're going to have like zinc ion in a reaction, and its charge is 2, right? Plus 2. All right. So if that was in here, you would see. So the atomic monoatomic ion, its oxidation number is going to be the same as the charge. Now, the last one is what you work with last, and that's why it's in order. The sum of the oxidation numbers for a polyatomic ion is going to equal the charge on that ion. Okay. In the example that I have in my notes, I have a polyatomic polyatomic compound there. Okay, I have a compound, and there's no charge on it. So that would mean that that full thing, the charge would be 0. All right, the full oxidation would be 0, and everything in that needs to add together to get there. Right. So here, that overall, so there's not a charge on here. So overall, this hydrogen bromide is going to have a charge of 0 overall. And the hydrogen iodide is going to have an overall charge of 0 as well. Okay. But notice, that in that ion, the hydrogen is +1, and you only have 1 iodine to go with that. So that's got to be -1, because +1 and -1 added together equals 0. Same thing here. Okay. So that bromine over here is -1. Okay. But here you started off with bromine as 0, and now it's gone down to -1. So you decrease the oxidation number. So bromine's been reduced. And over here, you've increased it. So you've been oxidized over here. All right. And in my notes, you can see how we do this step by step. And you basically go with what you know. All right. And like I said, it's quite easy if you do some practice. All right. And again, I'm not going to do a lot of that with you. I just want you to be aware that this is the other way to do it. But fundamentally, I want you to understand that there's a movement of electrons in this process. Okay. Yeah. Okay. Now, so like I was saying before, so an oxidizing agent is something that is really good at oxidizing. They are reduced. And a reducing agent is really good at reducing. So it accepts electrons. So, it donates electrons, so it's going to be oxidized, all right? So oxidizing agents cause oxidation. They're going to be reduced because they love to take those electrons. Reducing agents cause reduction. They're really good at giving away those electrons, so they are oxidized, all right? And like I said, I sort of alluded to, chemists have been working on this for quite some time, and there's actually a hierarchical level of, in tables set up so that chemists can find out how good something is at accepting or donating electrons, and that's really important when you're setting up a battery. So I'm going to, which we're going to, just get into. All right. Now, there's all kinds of examples of redox chemistry, around, like I said, batteries, which we're going to discuss. But another kind of neat example is photochromic glass. And I know you've all seen this before. So people who have glasses that darken when they go outside. And indeed, I have a pair of reading glasses that I'm actually computer glasses, but they have that, we used to call it photo gray. So I have these so I can read outside in the summer. It's really funny because, in the summer, the sun is just bouncing off whatever I'm reading. And it's just really crazy. But my reading glasses will darken when I'm outside. And it's because they have this redox reaction that takes place in there, in the lenses. All right. And, that darkened color is actually silver solid. And when you're not in the sun, that silver solid goes back to silver ion, and it's not, it's not gray anymore. All right. So how it works is that you have the silver, and you also have copper in there. And I have the reactions, outlined in my notes. But basically what's happening, and there's a bit of an energy input into this, and it's driven by sunlight. Okay, so what happens, and you can see it in my notes, right? So you get input of energy. What's going to happen is that that chloride, right? So you'd have this copper 1 chloride, and if you look on your periodic table, you know, chlorine is going to be -1 because it's in group 7. And what happens there is that that chloride is going to give off that electron, and and it's going to become chlorine neutral, and silver ion that's in your glasses when they're clear, it will accept that electron and become silver solid, right? Now, it's really important that you know, when you don't have sunlight, that you can reverse that reaction. So it is reversible, and this is why you need the copper. Okay, so copper is a transition metal, so it has a couple of charges that it can take on. Like I said, it's really weird because of their earlier in the course, I was telling you that the placement of the electrons in the orbitals is such that it can have 2 different charges. So copper 1 or copper 2. So what's going to happen without sunlight is that the copper 1, and as you can see here, I have copper 1 chloride. That copper 1 is going to be able to take an electron from chlorine and actually give an electron back to the chlorine, and it's now going to be copper 2, and then you're going to regenerate then your chlorine ion, so Cl minus, right? And then your copper 2 is going to, you know, totally love to take that electron back from your silver, and so it'll take your silver solid, and you'll regenerate your copper 1 and your silver 1, and which is now clear, and that will then let your lenses get clear. All right, so it's really clever chemistry, but basically you need the electrons moving between these, you know, 3 substances. So chlorine, copper 1 and 2, and silver. And it works really nicely because copper is a transition metal, so it can have those 2 charges. So the chemist that figured all that out was quite clever, obviously, and it's very, very useful, right? Okay, so let's go back, and we're going to start talking about these batteries. So electrochemical cells and batteries. So we're going to start off, we're not going to have a battery right now, but I want you to understand that, you know, many of the substances used in specifically, you know, batteries that are generating electricity on their own, right? So they have these spontaneous reactions that take place. They're redox reactions. And the difference here is that we can use some sort of metals that we use as electrodes, and they will gain or accept, gain or donate electrons. And we have names for them, right? So the anode, and I'm going to try and stay color-coded here. So when I see blue, it's going to be oxidation, red, reduction. So the anodes are where oxidation occurs, and the cathode is where the reduction occurs. So anode, oxidation, cathode, reduction. And one way to remember that is when you see the vowels, so A and O, so anode, oxidation, and cathode. So now we've got the consonant, so cathode and reduction, so C and R, all right? So those 2 go together, and the vowels go together, right? I've seen other things like using an-ox and red cat or something like that. That's another one, if that works for you. But hopefully that makes sense. So try to remember that. Anode, oxidation, cathode, reduction. So basically what's happening here is that certain metals, in this case, we're looking at metals, will spontaneously react, and electrons will flow between them, and they will then cause this chemical reaction, right? So here's your redox reaction, and you have, I'm showing the 2 halves. So here, this is a very common one, copper and silver, or copper. Silver is a little expensive, so sometimes you see copper and aluminum or something like that. zinc and aluminum, but here for this case, we're doing copper and silver. And here we have this oxidation. We have copper solid will love to donate its electrons and become copper 2+. And silver, on the other hand, so silver ions would love to accept those electrons, and it would then become silver solid, right? So if you're looking at this, the electrons are going to flow out of the copper, and then eventually you're going to get silver solid, and the silver solid, so you have silver salt in solution here, and you're going to have that silver then become a solid, and it will deposit itself on the copper, all right? So overall, you have copper solid, silver salts, copper, well, a silver copper salt here in the solution, and then you're going to have the silver solid on the other side, all right? So here you can see that there's a flow of electrons. So the electrons are going to move from the anode to the cathode. So in this case, we don't have a battery here. It's not really doing any work for us. You've got a straight up redox reaction, and you can see that there's a flow of electrons. All right, so they're going from the copper to, not to the silver, but they're going from the copper to the silver ion, and then making the silver solid. Okay. Now, what you can do now is that you can then put in between these. So you separate the reactions out, and in between put a conductor, like a wire of some kind, all right, that will allow those electrons to flow from one reaction to the other. So in this case, you've got everything all mixed up together in one tube. But if we separate them out, the electrons are going to flow spontaneously from one reaction to the other. Okay, so there's a couple of, well, obviously quite a few stages between looking at reactions and understanding how they worked. And in your book, we just bring up these two people because you've got Galavani and Volta. So volts are how we measure the strength of the battery, or the pull of the battery. And Galvani, a galvanic cell, this is like when we're talking about these flow of electrons, so spontaneous movement. So this is named after these, so it'd be a galvanic cell that we're talking about. But Galvani and Volta, those are the two individuals that were involved in studying these. And here you can sort of see just a bit of the history. And I don't, obviously there's some, we're taking this completely out of context, but we can look at some of the observations. And so Galvani, and this is really bizarre. I have no idea why he took a frog's leg and attached a wire and rubbed it across a metal, why he did that. But anyways, and like I said, sometimes these things happen by accident. And again, obviously at this time, they did not know what the atom looked like either, so they would not know about electrons. But like I had mentioned before, they were playing with static electricity and a lot of it, and they were using these electrochemical cells and didn't really understand how it worked. Okay, so why he did this, I don't know, but he hypothesized, or he thought, that the leg was generating some sort of current. And if you know anything about physiology, you know that there's lots of electrolytes here. All right, so if you look back here, you've got these salts in solution, and if you remember, those carry a charge, and that's an electrolyte. We mentioned that earlier in the course, right? So your body is full of salty stuff, all kinds of different salts, including salt, but other different types of salts, and it is a good conductor. So if you rub this metal wire on a screen, it's going to generate some sort of a current, and indeed the frog leg would be able to move that. And if you know anything about the body, which that's sort of the other thing I teach, you'd know that there's biochemical currents that cause muscle movement, and he observed that the frog leg twitched. So he said that this leg is generating electricity, actually it was conducting electricity, all right? Now, Alessandro Volta disagreed with him, All right, and he did his own studies to prove him wrong, I guess. I don't know. I don't know really how all of that interaction went. But he was the one that developed the first battery. And he used silver and zinc, all right? And he put them in a brine or a salt solution. And you know why he did that, I don't know, but you can see that he had a stack of them. And in lab, we do like a coin battery sort of idea. But it's working on the spontaneous movement of electrons between the silver and the zinc. And again, I don't know their the oxidation numbers for these off by heart, but obviously one is going to have a better pull for electrons than the other, and you can then calculate the charge. And for each set of disks, it's like stacking a whole bunch of batteries together, so that you would be able to get more current with that. Okay, and again, not knowing what this was, it was just an observation. Like it could do work. All right. Let me just make sure I haven't missed anything. Okay. All right. So now let's look at a galvanic cell or a battery. All right. So the things that you have to remember is that first of all, you have to separate the reactions and connect them by some sort of a conductor, all right? So a wire of some kind, very often use copper wire. And then the other thing you need to do is some way of balancing the reaction, right? So that to complete the circuit, all right? And what's gonna happen then is if you separate the reactions, the electrons are gonna flow, so in this case from copper to silver, and they're going to go and if you put something in between, you can use that flow of electrons to do work for you. So light up a light bulb or charge your phone or whatever it is. We'll talk a little bit more about that when we talk about different batteries, right? And then the electrons are going to go here. And in this case, the electrons want to go from copper solid, all right, to actually silver ion, all right? And what's going to happen then as this happens is that as these electrons are going to go through here, this silver ion is going to be reduced and be deposited on the silver metal bar here. And on this side, as you are moving electrons, the copper solid is going to become copper ion, and that's going to go out into solution. So what's going to happen here is that you're going to build the electrode, and on this side you're going to lose it because this is slowly going to disintegrate. Now, what's going to happen is that you're going to have a buildup of positive charge on this side, and you're going to have a buildup of negative charge on this side as the positive ion in the salt is diminishing. And this causes a problem. So you need to have some sort of way for this negative to neutralize out the positives on this side. So you could have a porous partition and allow for this to actually go through, but usually that's not what's done. What they do instead is make a salt bridge, and that's what we did and we're going to do in lab. And in that, you're going to have a salt in here, and then on this side, the negative ions in the salt bridge are going to come over here and neutralize that buildup of charge here, and then the positive ones are going to neutralize the negative on this side, and this is going to complete the circuit. But eventually, once you run out of copper, the cell will stop, all right? So eventually, no battery runs forever, at least as far as we've been able to create so far. And you can watch these videos, and it sort of shows you how all this works in an animation, and I always find that really helpful. And I'll be honest with you, I find teaching this really difficult. I mean, redox good, this is fine, but once you get into the different types of batteries, it starts to make my head hurt a little bit, because sometimes the chemistry that's going on there is quite complex. And I'm someone who really wants to know exactly how everything works. And at some point I have to just step back and just, think, okay, so there's, dedicated chemists, physical chemists, and, who worked all this out, and I just have to defer to them. And that, indeed is, the first example here. the very simplest battery ever, the dry cell or the galvanic or voltaic cell, which are very, very common batteries. But you know what? The chemistry is not that simple. So there's a few reactions that take place. At least to me, the chemistry isn't simple. So I've included this video here so you can watch it. And I've only been able to find this one video that actually explains all the parts. Because there's some parts here that if you just look at it, and I'll explain it in a sec. But basically, when you're looking at a typical dry cell, and this is the most common type of battery, so it would be like your alkaline batteries, the ones that you want to recycle, because sometimes they have nasty stuff that you don't want getting out into the environment. But basically what you have is you have your anode and your cathode. So in this case, your cathode, where the reduction is taking place, is a graphite rod, okay? And your anode is the zinc. It's the case out here, all right? And we want to generate the flow of electrons, right? So, so we have to separate it. So we have a porous spacer that's separating this. And this is what gets kind of weird. So around the graphite rod is a paste. And this paste, and there's just a little bit of water in there, all right? So there's a little bit of water in there, and it provides the reaction reduction for the cathode. And this is the part that I find really weird. So basically what's happening is that the electrons are going to be are going to serve to reduce this, okay? And they're surrounding the graphite rod. So notice that in the chemical equations here, you don't see any carbon. So basically what they're doing is they're accepting the electrons that are being generated at, in the electrons are being passed from the reduction reaction to between the reduction reaction and the carbon rod, all right? And if you look at the video, that explains it kind of nicely how it works, all right? But the overall chemistry, right? And this part is probably the easiest one to understand, is that you're going to take zinc and you're going to oxidize it. And so it's going to release the electrons. So, so the electrons are coming off of the zinc, and they're eventually going to get to the carbon rod. But the way it works is that it's going to interact with the manganese. All right, so you can see here, there's a carbon rod, and you've got this paste, and this paste here has a mixture of manganese oxide, okay, and you've got your electrolyte, all right? So very often the electrolyte is ammonium chloride, or in an alkaline battery, that ammonium chloride is replaced with either sodium hydroxide or potassium hydroxide, and they're basic, all right? So these are basic, that's why it's called an alkaline battery, all right? And then you also have some graphite powder in here, all right? So, so this whole thing is this dry cell. And so the overall reaction, okay, is this one here that you can see here. And your zinc ion is going to be balanced out with oxygen. That's basically in the water as well. So it's not as simple and clean as this reaction here for this electrochemical cell, all right? But this is a very classical type of battery, and this is the overall chemistry that's involved. You don't need to memorize it, but since this is such a common battery, I wanted to show you what these reactions are, and then the overall reaction. But again, remember the zinc is the one that's being oxidized, so it's producing the electrons, and they are going to interact with the manganese. And manganese is one of those transition metals, so it has several different charges that it can take. And you can if you want to work out the oxidation number, you can, but basically going from +4 to +3, and you can see that it's going to be reduced. And we're able to harness that flow of electrons between the zinc and basically the carbon rod for the manganese, all right? And then the electrolyte is a base, classically ammonium chloride, but like I said, sodium hydroxide is also used, and that's why we say these are alkaline batteries. And that's quite cheap, and I think that this is probably the sodium hydroxide or the potassium hydroxide is much more common than using the ammonium chloride. Okay, all right, so hopefully that sort of explains it. But this we say is this dry cell, and I've noted here that this is a galvanic or a voltaic cell. And if you look on page 5, I have some extra notes here. So a galvanic or a voltaic cell generates electricity simply by spontaneously by the types of reactions that we have, and we're separating them from each other so that the electrons can flow. Now, if you know anything about batteries, we know that there's another kind of cell you might have heard of, and that's an electrolytic cell. Now, an electrolytic cell, that one uses energy input to force a reaction that isn't spontaneous. So it's basically powering the reverse reaction, all right? And where you see that is with electroplating, for example. So if you want to, say, coat something with chromium or chrome, or coat it with gold or silver, you can input energy and force a reaction to take place and cause that metal to deposit on something it might not otherwise deposit on, right? So, I mean, here with this one, you could see that here we're actually plating silver on this copper, all right? But you might have a different metal in here, so you might have some really cheap jewelry, and you have a really cheap metal here, or some sort of weird, mix of metals that's really cheap, and you want to coat that with silver so it looks nicer, and then you could input electricity to force the electrons in that direction and coat that with the silver solid from a salt, all right? So that would be an electrolytic cell, all right? And you're going to input energy into to force the reverse reaction. Now, why am I bringing that up? Well, the other very common battery that we have, say, in our car is a lead storage battery, all right? And in here, that when your car is driving, it can charge up your battery again, right? So you need a bit of a discharge when you're starting your car, but then when your car is running, you can recharge it. So the way it works, all right, is that you have this lead storage and you can see the reactions. So the discharge of that battery is a galvanic or a voltaic cell. So it goes by either of these names because you've got Galavani or Volta, right? So this is what we call the spontaneous reaction. And here's, you've got your lead and you've got your sulfuric acid, and the spontaneous discharge reaction is what you see here. Now, recharging, though, you're going to force it to go the other direction, all right? So the recharge is electrolytic, and in that case, you're going to input energy, right? So from the drive of the car, right? So you can generate, when you're burning your fuel and you're turning your wheels, and that's going to generate energy that you could put back into the battery, all right? So the recharge is what we call electrolytic. So electrolytic, a current is applied to drive the desired reaction, to force those electrons in the direction that would spontaneously occur, but you can then recharge, right? And not every type of battery is rechargeable. Like this one, like the ones we were just talking about, the dry cells here, this is not one where you can recharge it, all right? Why that is, I'm not quite sure, but it's probably because it's, the reaction is quite complex here. Not that this one isn't, but some things you can force in one direction, and and other ones you can't. So not every battery is rechargeable, as you said. So where do you see electrolytic cells? Do you see the electrolytic when you're forcing the reaction back on a rechargeable, or when you're coating something, right? So when you're coating metal on stuff, right? Yeah, well, there's a question in your lab homework when we're doing this about, you know, how do you know if something's been coated? So something to think about here, okay? Now, other types of batteries that are very common are nickel cadmium. Now, again, understand that these are gonna, you know, they're working the same way. You're just using different compounds or metals to, and different types of salts in your salt bridge. But basically, you're working from this spontaneous reaction that electrons want to move from one to the other, because one is a really likes to be reduced, or it's a good oxidizer, and the other one is, you know, the opposite. All right. Now, when it comes to rechargeables, these nickel cadmium, these are the most common ones, right? So then when you're going to recharge it, you're going to do the electrolytic reaction and force it in the other direction. All right. And as you know, this is, you know, not limitless. Eventually, it's going to, you know, your rechargeables are not as rechargeable anymore. All right. And you eventually have to replace them with new rechargeables, right? So this is an important thing to understand. So, you know, the chemistry here isn't completely perfect, right? And the reasons for that, you know, we can talk about later. Okay. Yeah. Okay. So other ones, lithium batteries. Why lithium? Lithium is really popular because it's good for recharge. They last longer. It's a really good kind of compound to use. So lithium, of course, mining it isn't nice. You probably might have seen pictures of the open pit mines that they do to get this lithium, but it's got some positive attributes. So it's lower in density and higher in voltage than that nickel cadmium, all right? So you can power more stuff with a lithium battery. You know, they're better at recharge. The other thing, though, is that if you combine lithium with a polymer, it can be shaped, which is another really nice thing, because you can, you know, you don't need to have these, you know, fancy cells. You can have the battery take the shape that you need it for, say, your device. So that is kind of a nice thing about them. All right. Now, in my notes on page 6, you're going to see that I did a transition between the nickel cadmium batteries and the lithium ion batteries. Okay. So you can see in the rechargeable, so nickel cadmium, very, very common, right? Rechargeable. But there are other ones that are used. So there's like a nickel manganese hydrogen one there. Lithium ion, lithium polymer. So lithium ion, that could be lithium and iodine, lithium and sulfite, lithium iron sulfate. And you can see that they're used, sulfide, I should say, iron sulfide, in cameras and in different places. You can sort of see that in my notes. Lithium iodine in pacemakers, all right? So you can see these different types of lithium salts that can be used, all right? And then, like I said, lithium ion polymers are really easy to shape and fit in as you need, all right? But again, rechargeable. Now, the next thing is fuel cells, all right? And there's a lot of talk about fuel cells. Now, the important thing here, the oxidizing agent is typically oxygen, all right? Now, the reducing agent is supplied by fuel, all right? So I asked this question on a test once, and a student said, oh, well, the reducing agent is hydrogen gas. And I said, you know, and they got it wrong because I couldn't find it. Basically, the reducing agent is any fuel. One of the fuels they want to use is hydrogen gas, right? So they use this in space and stuff like that. And, you know, indeed, when we're talking about fuel cells, this is sort of the fuel that they are imagining using. Now, why do they want to use fuel cell? Well, because the nice thing here is that when you're using a fuel cell, is that you're not making carbon dioxide, right? You're taking hydrogen gas in this case, you know, if this is the fuel, so you're taking a fuel, so hydrogen fuel, and you're combining it with oxygen, and you're giving out water, right? So, and that's sort of the desire here. So, at the anode is where you got your oxidation. So you're going to oxidize that fuel. So you're burning it, right? It per se, right? Remember, burn and unburn. You know, you don't see fire there, but it's that kind of thing, right? So, and then the hydrogen is going to give off its electrons, and it's a good reducer. It likes to do that. It's going to give off its electrons, and oxygen is a good oxidant, right? That's why it's oxygen. And it will then take those electrons and it will balance out with the hydrogen. The electrolyte tends to be some sort of base. Okay, let me just see what I wrote in my notes, if I actually wrote it down. Yeah, so it's like some sort of hydroxide. So if you look on page 7, a very common one would be potassium hydroxide as the electrolyte here. So it will then, easily be able to allow for the transfer, and you're going to then, pump out water. Okay. Now, so the fuel then, like I said, is oxidized at the anode and reduced at the cathode. And the electrons then flow through here and allow this to do work. Now, there's some issues with this, all right? So, I wrote down in my notes and in the video here, Japan is a real proponent of using fuel cell technology. And, but Elon Musk does not support this idea. And you can find all kinds of videos of him talking about that, which is why I brought him up. But what is it about the fuel cell that he doesn't like? So there's a few things. And first of all, the efficiency issues. So when it comes to, it looks great, right? But actually to make hydrogen gas is not the easiest thing to do. All right. So depending on how you're trying to do it, so you might need to input some energy. So there's this idea of making a hydrogen from water, right? But you can see that's the reverse reaction. And in that case, you're going to have to put energy in to get that, right? And there's other ways of generating it, but that's one issue. The other thing is the infrastructure isn't around, and yet. And for some reason, these cells don't have a long lifetime right now, comparatively. So there are issues with it, and that's not to say that things will not improve. And I mean, obviously in Japan, where they are promoting the idea of a fuel cell, they're going to be doing lots of work to improve these efficiencies. Okay, so the science isn't perfect yet. Oh, the other thing, in order for this reaction to take place, we're going to talk about catalysts shortly. But there's a catalyst here, and the catalyst here sort of facilitates this reaction to drive it forward. And you can see here that I wrote down platinum, nickel, or rhodium as electrodes or as the catalyst. So there's some precious metals involved with this, which when we were talking about green chemistry, doesn't make it as green, right? So here you're not having CO2 output, but you have this issue with the inefficiency of the cell, as well as the use of the catalyst, which tends to be these precious metals. So there's issues with it, all right? But anyways, fuel cells. Now, other types of redox. So we're going to go through a few different ideas here, and hopefully this will help you appreciate other types of redox reactions that are going on, right? So corrosion. Rusting of iron is a big redox reaction that causes a lot of trouble. I wrote down in my notes that it's $275 billion in costs to replace rusted iron. 20% of iron and steel production goes towards replacing these products. So this is a major issue, corrosion, but it is redox, right? So basically you're taking iron solid, and you're oxidizing it. And you can see you have ferrous and ferric hydroxide, and over here. So you can see, and again, iron is a transition metal, so it can go from 2+ to 3+. And it does that with exposure to water, And in that water, and you know, up here in central New York, it's salt on the road. So we've got water and salt. So here's your electrolyte that's going to drive this reaction. And you're going to get a deposition of this ferric and ferrous hydroxide on here, which is, you know, rust, and you see it there because you've got the iron in there, and you can see the redness of it. Okay, so this is the problem with this in the breakdown of the metal that is the consequence of it. So basically you're taking, just like we had on the oxidation side of our batteries, let's go back, right? You're going to be removing the electrons here, and as you do so and you make this ion, you're going to be losing this metal. Okay, and that's how that works, and that's driven by oxygen in the atmosphere with water, and of course all of the salts that we have in the atmosphere as well. Okay, because they will behave as the electrolyte. So aluminum also corrodes. All right, it's actually, well, in theory it's more reactive than is iron. But the interesting thing about aluminum is that once it gets this coating of aluminum oxide is actually very tough, and it's hard for air and water to get through it. So this is why aluminum products last longer. They don't tend to break down, even though they're more reactive than iron, because of that aluminum oxide. So it's sort of like the product of the oxidation acts to then protect the aluminum underneath, which is kind of an interesting idea, right? So, and this is the benefit of using aluminum for pots and cans and that kind of thing, all right? Another one that you probably have seen is the tarnishing of silver. And so this is now on page 9 of my notes. So this one, I don't have the chemical reaction on the slide here because it's not a matter of understanding that, but you'll see as we go through the course that there's hydrogen sulfide in the atmosphere, and it reacts with a redox reaction with silver solid, and it will make aluminum sulfide and hydrogen gas, which is kind of weird. And that reaction then will cause your silver to break down, all right? And eventually it's going to oxidize, all right? And it will tarnish, and it's not pretty, all right? So the tarnishing of that will we try to get rid of that, all right? Because it's not attractive. So the way it works then is that you want to try and get your silver solid back, or you want to get rid of the silver oxide or the silver sulfide that's coating your silver. So one way to do that is to polish it, but if you do that, you're actually going to lose the silver, right? So it will restore the shine, but you're going to lose the silver in the process. Okay, but the other way to do it is to allow for a reverse reaction. And you can use aluminum. So you can see these aluminum trays, and they used to sell this at like fairs and stuff like that. It's like this magic plate that would, restore your silver. But the interesting thing is that this is the preferred way, because the idea then is to keep your silver and you don't lose it. So I put the reactions in my notes. So what it's going to do then is going to take the silver sulfide, and it's going to react with the aluminum solid, and then the aluminum then is going to take the sulfur. And in aluminum, while it does cost something, it's not as expensive as silver. So you're just exchanging the metal with the sulfide for the salt, and in so doing, you're not going to lose your silver. Right, so it just gets deposited, it gets converted back to silver solid, and you're not going to polish it away. So that's sort of the idea here. And eventually you'd have to get a new aluminum plate, but that's easier to replace than your silver, whatever it is that you're trying to get rid of the tarnish. All right. So like if you're interested, you can see that chemistry on page 9, all right? And here, you put a bit of bicarbonate in there to act as the electrolyte. So again, it's all about moving those electrons. In theory, you could, I don't know if it would generate much of a current, but the sodium bicarbonate helps to be to mitigate the excess charge to keep this thing going. All right. Another example are explosions, right? So bombs, right? So they are. I'm not talking about nuclear bombs, that's different, as we already know, but because that's a nuclear reaction. But if you're talking about typical chemical kind of bomb, this is a redox reaction, and this is an example here. And again, you've got a fuel that's involved of some kind. So these chemical explosions can be the result of redox. So how these work is that first of all, the reaction is very efficient, so it takes place very, very quickly when you combine your two reactants or more reactants. And the other thing is that it involves a dramatic change in volume, all right? So, and this is the example that I'm putting up here. If we look at it, so ANFO, so that's ammonium nitrate mixed with fuel oil. That's what that stands for. All right. So this is the reaction. So you're basically using fertilizer here, and you've got a fuel. Anytime you see something with lots of carbons and hydrogens, it's some sort of fuel. There's lots of energy stored up in there. And notice a couple of things here. All right. So when you're looking at this, on this side you have a solid and a liquid, and as you know, a solid and a liquid have specific shapes, right? The liquid will take the shape of its container, a solid is what it is. But notice on the other side, you're converting this to gases, right? So gases, of course, expand to fill their container. And if they're not in a container, they're just going to keep expanding outward. So, so this is part of the explosive reaction that's taking place here. The other thing is notice the number of moles that you have. If you've got 53 moles to start with, and over here, I think I did the math, it ends up being 191 moles on this side. So there's a huge expansion of product on this side. So that's why, and it's very rapid, all right? So it's a very rapid reaction, and that's why it's so explosive. And I also listed on page 10 some other types of explosives. So nitroglycerin, which is dynamite, ammonium nitrate, fertilizer. So that's what we're looking at here, ammonium nitrate, trinitrotoluene, TNT. So that they used to use in mining a lot. They probably still do. Yeah. So there's another one that, because I like watching science fiction, and there's also one. I was watching Stargate, and they always use C4. I don't know what C4 is, so if you want to look that up, you can. But obviously, there's another one, and it's a solid, and it expands, obviously, and explodes. So whatever C4 is, like carbon, 4 carbons. I'm not sure. Anyhow, I could look that up. But anyways, explosions. Right? I'm going to guess that's going to be some sort of redox reaction there as well. All right. Now. Oxygen is the most common oxidizing agent, right? It's the oxidant, and it's in the atmosphere, all right? And something I want you to appreciate, I'm hoping you're going to appreciate as we go through this course, is that you yourself are a electrochemical cell, right? We saw that back here with the, and I sort of mentioned it with the frog leg, right? You're driven by electricity, right? There's electricity flowing through you all the time, right? And this is how, if you've ever had an ECG done, you get hooked up to a bunch of wires, and they can measure your current that's coming through your heart. So you are an electrical being, all right? And in there you have the movement of electrons that's doing that for you. Those that energy to drive those electrons is stored up in the chemical bonds of your makeup, all right? And I'm going all biochemist on you. And you have a way of storing that energy, and that your storage is ATP, all right? But where does it come from, all right? Well, it comes from your food. And your food comes from ultimately, you know, plants or animal products. And where did that energy come from? Well, it come from the sun, right? And what I'm hoping you're going to see at the end of this is that, you know, the whole planet is a large rechargeable battery. All right. So let's start with the oxygen side, right? So we've got oxygen. It's the most common oxidizing agent. 20% of the air and about 50% of the Earth's mass is oxygen. In the atmosphere, it can exist as O2, as you know, but also as ozone, O3, right? And it reacts, right, with metals and nonmetals, and it forms oxides. Now, in your body, you are going to use that oxygen, right? You inhale oxygen gas along with all the other gases in the atmosphere. Actually, it's mostly nitrogen, but it's not very reactive, so we don't use it. Unless you're under pressure, you're a diver. What's going to happen here is that oxygen is going to be the oxidant that's going to drive a bunch of chemical reactions in your body, all right? So, and I've sort of shown it here. You might have learned about this glycolysis. Basically, that's, you start off with a food, so say sugar, and it goes through a bunch of chemical steps. And as it does so, it's gradually going to release electrons, and those electrons are going to be used to harness energy. And that energy is going to get stored up in your battery, which is ATP. Okay, so adenosine triphosphate. And you're going to make a waste product in doing this. You're going to exhale CO2, right? You take in oxygen, exhale CO2. So you can see the oxygen has been reduced to CO2. And you're going to pee out the other waste product, which is water, right? So oxygen is going to be reduced, because it's an oxidant, to water and CO2, all right? And do I have that reaction written out on this? I do. So you can look at that on page 11, right? So you can see the waste products and, the oxidant. And oxygen is going to drive this process by attracting electrons to itself. And your body is really well set up to do this, okay? So oxygen, most common oxidizing agent. And like I said, it also exists as ozone. There is some ozone down at our level of the atmosphere. We're going to talk about the levels of the atmosphere when we get to air, our air chapter, but we're in the troposphere. Ozone at our level is toxic, right? It's because it's a powerful oxidizing agent, right? This is why we can use it to kill bacteria, because it's really damaging. All right, but we need it up in the stratosphere, right, up there, because it is a good oxidizing agent. It accepts energy in a way, so it can absorb UV light. Not UVA can get through, but different wavelengths of UV, ultraviolet. Remember, in your electromagnetic spectrum, there's a range that's UV. And I'm going to show you that chemistry later, how that works. But basically, ozone can take that energy and make oxygen. And so it's very important because it protects us. And we'll talk later on about how there are certain gases or chemicals that we used to use that would deplete that ozone layer, because ozone will react with other stuff. And this was making a huge problem. And when I was younger, this was an issue, and the world worked together in that case to try and restore the ozone layer, all right? Now, other common oxidizers other than oxygen that you might encounter, hydrogen peroxide in your house is a good disinfectant when you have like a sore or something, or a wound. You also encounter it if you dye your hair. Very often you've got to get rid of the color, so you're going to bleach it out with hydrogen peroxide first. Potassium dichromate, it's not as common in your house, but it will oxidize alcohol and turn green. So it's used in a breathalyzer. And the greenness can then be used, I assume, to calculate how much alcohol you have in your breath. Benzyl peroxide is an antiseptic, right? And also used to treat acne, so because it kills the bacteria. Chlorine, of course, can be used to treat water, right? Drinking water, and get rid of bad stuff. And we'll talk about later how that works. But again, it's an oxidant, will kill stuff. and other bleaches, right, you use on fabrics, because they are oxidants, all right? So they'll get rid of the stuff that's making stains or whatever, just because they will change the chemical that is there. Now, reducing agents on the other side, okay? So we already talked about hydrogen, and of course that's a really good reducing agent. But we also have metals can be good reducing agents, and we'll talk about this particular one later in the course. Carbon, right? So carbon can be, you know, produced by pure carbon, coke, can be produced by heating coal, and it's then used as a reducing agent for smelting. So we're going to, you know, talk about this later on. Bad byproduct, of course, is carbon dioxide. Aluminum can be used to reduce chromium oxide, make chromium metal. All right, so you think plating, right? So that would be a good reducer. Then, so you can have aluminum and then plate chromium. So you can at least imagine that reaction. In photography, I know we don't do this as much as, you know, it used to be, but this, you know, when you had your film, parts that weren't exposed to light would be darker and it would deposit the silver solid. So silver ions in silver bromide are also really good as reducing agents. All right, so yeah, okay. So reduction in photography. So silver ions in the silver bromide, black and white film exposed to light are reduced back to silver metal. All right, so silver bromide. Now, antioxidants are obviously, you know, things that are going to fight oxidation. So here you have, and let me make sure I catch up with my notes here. Okay. So here you've got this situation where you want to get rid of that electron. So you're going to use an antioxidant to do that. So it's going to accept that electron. So it is a reducer. And we've talked about how this works and why we want to do this before in this course, but now I want to sort of put it in the context of redox. So really good antioxidants are vitamins, foods, and in your cells, again, because you've got a lot of chemistry taking place in your body, you also want to be able to protect yourself from antioxidants. You've got actual organelles in your cells that contain peroxide and the peroxisomes, and they will help you do this. So these are organelles that have enzymes that will then break down these free radicals, all right, these peroxisomes, all right. I said hydrogen is a very, very common reducing agent. It's really good for both metals and nonmetals. Hydrogen gas can be produced by reacting with zinc and hydrochloric acid. So there's a way of producing hydrogen gas if you're talking about making that for fuel cell, for example. But again, now you're dealing with hydrochloric acid. Anyhow, these hydrogen can reduce these metallic oxides back to their metals, all right? And then in order to facilitate this, you can also, again, use a catalyst. We're going to talk about catalysts in a sec. But again, hydrogen as a reducing agent. Yes. All right. Now, going back to what we were talking about in terms of oxygen and producing energy in the body. And I said to you, I'm hoping by the end of this, you'll see that the Earth is like one big battery with many parts, right? So I mentioned to you, where do we get that energy that we are harnessing and putting into our ATP? Well, it's from our food. Our food is from the plants, right? So we already talked about this part here, right? So you got your foods is basically sugar. You're gonna take that oxygen. Remember I said the electrons that are being pulled to the oxygen, and you're going to get rid of CO2 and water, and you're going to store that energy as ATP. So this is one side of the equation. But there is a recharge that happens, right? So where does that energy ultimately come from? Well, it comes from the sun. And plants harness that energy and incorporate that into their structure, which we then consume. But how do they do that? Well, you see that we produce CO2 and water. Well, the way plants do that is that they take CO2 and water plus energy and make food, and they give off oxygen, right? So you can see that the sun then recharges our Earth battery, if you want to think about it that way. All right, so we have this amazing electrochemical cell that is the Earth that's taking place here. So the Earth and the organisms living on it, and this really shows to you how connected everything is in terms of, and you're going to see other examples of this in this course, but you can really see how connected we are as if you look at it in terms of a redox reaction. All right, so photosynthesis. That's this part here. Okay, so here is like what we do, and then plants are doing the photosynthesis part. Okay, so a series of reductions, and then whereas here it would be a series of oxidations. All right, so we do a series of oxidations, and plants do a series of reductions. So the reverse reactions of photosynthesis are exactly opposite to what's taking place here. Okay, so hopefully you see that, and you find that I find the cool factor there quite extensive. All right, now I've mentioned the word catalyst quite a few times here, and we sort of talked about them a little bit so far, off and on, and basically what a catalyst is that it's going to reduce the amount of energy that's required for a reaction to take place. So usually a bit of energy input that is needed to get something going, but they're not going to be used up by the reaction. And they're very, very important in chemistry for a lot of the different types of reactions that we talk about. Now, how do these catalysts work? Okay, so we already said that they're not going to be taken up. They're going to lower the amount of energy input or the activation energy. But how do they do that? Well, they're going to strain bonds. They can help bring things together, put things in the right orientation so that they react. But when we talk about them industrially, all right, so now we're talking about, and very often, as I said, with the fuel cells, like a metal catalyst, like palladium or something like that, all right? So let's look at it in terms of our atom economy, all right, and how these things can help, all right? So here's two examples, and then the addition of and how that changes with the catalyst. So here you can see reaction of a ketone with sodium borohydride. Why you want to do that, I don't know. There's obviously some sort of purpose to it, industrially. And you can see if you just have the chemical reaction take place uncatalyzed in this way, using different types of salts, and using their redox chemistry, you can have an efficiency of 70%. Now, if you add in something much more simple, all right, so you're taking a ketone, and you're gonna, basically, because what you're ending up doing is you're hydrogenating this here, okay, so you've got this ketone and you've hydrogenated it, and doing this chemically without a catalyst is 70%. Now here, if you pretty much just take your ketone, and we're going to talk about how I know this is a ketone when we do organic, which is the next chapter. But this is a ketone, so double bonded O2 as a structure. And you just take hydrogen, and then you just lose that double bond. And you add in, instead of all of these fancy chemicals, and you add in a catalyst, you can see that my atom economy now has become 100%. So you can see this is very desirable. The problem here, though, in terms of the greenness, so it's green in that we're getting rid of all these chemicals and we're improving our efficiency, but it's not as green when we think about the fact that we're using this precious metal, all right? So, but we're going to talk more, we're going to build on this later, okay? But you can already see using a catalyst has made a great improvement. Now, similarly over here, we're doing an oxidation with potassium dichromate. I'm going to guess this is what I'm oxidizing here, because I'm going, I've lost hydrogen. All right, so that's a reduction. Or I've oxidized here because I've lost hydrogen. And you can see doing this the chemical way without a catalyst, my atom economy is 20%. Now, if I add in a catalyst and I oxidize this guy directly with oxygen, instead of using all these other chemicals, I'm not at 100%, but I've improved my efficiency, my atom economy greatly by doing the reaction in this way. Okay, so this sort of gives you a little bit of an insight as to why these catalysts are used. Okay, later on, to make this even greener, if I could get away from using these metals as catalysts, that would be even better, right? So we will get there later on in the course when we talk about other types of chemicals. All right. Okay. So I think that's it for this chapter. All right. So hopefully that was helpful. All right. Thank you.